talk a little bit more about configuration. We're going to talk about stereoisomers. I realized on Friday I'm kind of teaching this a little bit out of order, but I think it was good that the way it was presented. I think it was good because normally getting into configuration, that's like a weekend. So hopefully it made sense. We're going to talk about the number of stereoisomers, which we talked a little bit about on Friday. And then we're going to talk about enantiomers and diastereomers. So hopefully you got the packet that I sent. Was not really a package, just a document with the structures on it. And that way you can follow along a little better today. We've already been working on this Paxlovid molecule, and we have identified 1, 2, 3, 4, 5, 6 stereocenters. Is that right? Now, out of those 6, which ones, excuse me, which ones have we done already as far as configuration is concerned? We looked at this one, right?
Yes.
It was S, is that right?
Yeah.
And then this one was also S, I think. And this one here was S2, wasn't it? Is that right? And then what do we do? What about this one here with the nitrile on it? What do we say that was? R or S?
S.
Okay. So all of the ones that we excuse me that we looked at had a configuration of S. I want to do one of these down here, and then actually let's do them both, and that'll be all the stereocenters in this molecule, and that'll give a chance to talk about the number of stereoisomers, which we briefly introduced on Friday, and also give a chance to talk about mirror images, mirror images, and then diastereomers, which are not mirror images. So let's talk about that. So let's do this stereocenter right here, right? We know that the hydrogen is going to be 4, lowest priority, right? We have, if this is my chiral center here, where are my groups? Is this a group attached?
Yes.
Yes.
And this?
Yes.
Yes.
And, is that right? I'm gonna make that one pink. So these are my 4 groups. Yes. For this
Yes.
right here. All right. How do we prioritize this? There's a trap here, and I want to help you avoid it. I know when we look at the 2 carbons, let's just say here and here. Right? That's a trap. That branch is gonna give this carbon that's branched priority over the other one, even though it's bonded to a nitrogen. All right. That branching.
Which one?
So right here.
Okay.
Mm-hmm. So of these 3, we can look at, let's see. This is going to be my highest priority carbon right here. That's going to be 1. When we compare them, right now, if we compare these two, this one and this one, right? Of those two, one of those is going to be 2, one is going to be 3. If we look at this carbon here, the next atom bonded to it is nitrogen. On the other side, the next atom bonded is a carbon, right? So this carbon right here is going to be 2. And then this one will be by default 3. Are we following that or no?
Yes, sir.
I'm, and I prefer to do more complicated examples like this because when you see something less complicated, it's, basically like cake. So we start off with something more difficult. And then that way, if you see anything beyond this, it's not going to trip you up. All right. So that's 1, 2, 3. Is that clockwise or counterclockwise?
Clockwise.
Clockwise. And then H is where? It's already back, isn't it?
Yes.
So what is it?
R.
R. It's R. Excellent. So let me write that in. So this one is R. Good. Any questions about that? Yeah, the branch is it kind of throws it off, but just know that if you have a branched carbon and a carbon that's not branched, and when you comparing those two, that branched carbon is going to be higher in priority. Even though that other carbon was bonded to nitrogen, the first thing that you get to is the carbon itself, and one of them is branched and one isn't. So you don't have to go to the next atom in that case because it's already a point of difference with the branching. All right, everybody good on that? Let's do the last one. Go ahead.
I have a question. So the branch carbon will always have higher priority, or just
It's case by case.
okay.
If that let's say for instance, if number 2, if that was a oxygen, then of course oxygen is going to have higher priority. Right. But only when you're comparing carbons. If you have a branched carbon and an unbranched carbon, that branched carbon is going to have higher priority.
Okay, gotcha. Thank you.
Yeah, let me write that in too. That's a good point. Right. So if it's branched versus unbranched, that's going to take priority. But again, it's case by case as well. So, excuse me. All right. Let's do the next one. Can I erase the markings so it won't be too convoluted?
Yes.
All right. All right. So we've given that a configuration of R. Now let's work on the other one. This one. So we got hydrogen here, carbon here, and then a carbon here. Is that right? Those are my 4 groups attached. And we know the hydrogen is going to be the lowest priority group. So of those 3 carbons, which one do you think is 1?
The branch carbon.
The branch carbon. Good. So that's 1. And then between these 2, here and here, one of those is going to be 2, one is going to be 3 in priority. What do you think? So 1 is going to be a carbon that's connected to a carbon, This is also up top, also connected to a carbon. So is that cool? Do we stop? Okay. Do we have to find that point of difference? Because they're both carbons, yes?
Find the point of difference.
So the point of difference is going to be
Yes.
what? Nitrogen versus what? Oxygen. Is that clear? So anytime you have
Yes.
two same atoms, you have to keep moving along the chain until you find that point of difference. So in this case, it's nitrogen. The other side is oxygen. Oxygen has a higher atomic number. So that means that this carbon right here is going to be 2. And then by default, that's going to make this one 3. Yes, no?
Yes, sir.
Okay. Now, if we just count to 3, which direction is that going?
Counterclockwise.
It's counterclockwise. And H is all, excuse me, H is already back. Yes.
Yes.
So what does that mean as far as my configuration? Do I have to reverse it? Do I keep it? If H is
You
already
keep
back,
it.
I keep it. So if it's counterclockwise, that means that other stereo center right there is what? R or S? Counterclockwise, remember, is left-handed, sinister, and then right-handed or rectus is clockwise. So what would that be?
S.
S. Good. All right. Let me erase some of this stuff. All right. So we've actually determined the configuration of all of the stereo centers in Paxlovid. Right. Now, again, when we talk on Wednesday, I want to introduce y'all to this concept of reaction stereochemistry. So this actually matters, right? I talked about it Friday. In order to be able to make this, you have to have certain methods available to you to generate these chiral centers, right? I'm gonna talk about that on probably on Friday, so I'm gonna hold off on that. But this molecule with all these chiral centers is what you would call an asymmetric, or it's achieved by what we call asymmetric synthesis, right? That's a very, very specialized area of organic chemistry, where you actually use different types of methods like different types of catalysts or pre-existing chiral centers to actually generate a chiral center. So we're going to talk more about that later. All right, so let's push a little bit further. How many stereo centers do we have here total? We resolved all of them. So how many do we have? 1, 2, 3, 4, 5, 6, right? I mentioned on Friday, let's talk about this real quick. I mentioned on Friday the number of stereoisomers, right? Being 2 to the n, or n is the number of chiral centers. Right, so in this case, it would be 2 to the 6, wouldn't it? So that's 64 possible stereoisomers. 64. Again, that's a testament to the need for a very specific method for setting those stereo centers. So all the reactions that are used to make Paxlovid, and you saw if you looked at the bonus assignment, you've already seen one synthesis of Paxlovid. But all those methods that are used are used to generate this one isomer. This is the active isomer right here. All right. So 64 possible stereoisomers. Of those 64 stereoisomers, right? Some of those stereoisomers are what we call enantiomers. I'm gonna see if I can copy this right quick. Let me see if I can lasso it. Okay. You got 64 possible stereoisomers. So what I'm going to do is talk about enantiomers. Right? These are one of the, remember when we first started talking about chirality, one of the criterion was that the mirror images be non-superimposable. So enantiomers are non-superimposable mirror images. Right? So let me show you what that means. So if I took Paxlovid and I stood it in front of a mirror, right? And you don't have to write this down, but I'm gonna redraw it. I need to make that pen a little bit bigger though. I'm just gonna write this out as a nitrile. So let's CN. And don't worry about trying to match this. I'm gonna send you a document with the enantiomer so you can see it. So that's the same now. Hold up. So the enantiomer, and I know this is kind of sloppy, but just bear with me. I think my nitrogen is C. Yeah. Actually, hold up. I gotta turn this around. So this is what we would call, and again, this is let's see. Right, so this would be the mirror image. Now, it looks like everything is the same, right? All the stereo centers have the same direction, just like they are in the original. However, if I took the mirror image and basically let's say I put a spatula underneath it and flipped it over, what do you think is going to happen to all of your stereo centers? Are they going to stay the same?
Would the configuration be different?
On every single one of them. Every single one of them. Right? The configuration for an enantiomer, all of your configurations are going to change in that mirror image. Excuse me. Even though I have it drawn like this, right? This is one way to draw it. The other way to draw it, and I'm going to show you, I'm going to cheat right quick and paste this down here. What the enantiomer of this would actually look like is this. So this right here will be wedged. This will be wedged. These two would be wedged. And that would also be wedged. And then this would be dashed. That's what the enantiomer would look like. Every stereo center would be the opposite. Are y'all following? So the mirror image is the exact opposite of the original image. That's what an enantiomer is. So out of those 64 isomers, there may be an enantiomer and then multiple what we call diastereomers, which we'll get to in 1 second. Questions about that? This is the mirror image. And the reason we say it's non-superimposable, if you look at these two molecules, could I take the bottom, the one that I just drew, and lay it on top of the one at the top, and all the stereo centers match up?
No.
No, they wouldn't match because they all the stereo centers are going in different directions, right? Think about it. If you put, and I always do the same example, if you put your two hands together, like thumb to thumb, pinky to pinky, but then you took your right hand and you flipped it over to lay it on top of your left hand, what do you see? Are your thumbs in the same place? Or are they on opposite sides?
Opposite sides.
Opposite sides. That's what it means to be non-superimposable. If I just drew a mirror plane like I had initially, I just draw what I see, right? But I can also express that enantiomer in a different way by taking it and flipping it over. And when you do that, that's when you see all the stereo centers are different. So write that down. In an enantiomer, all of your stereo centers will change. They'll be the opposite. All right, all would be different. All right, any questions about that?
Excuse me, Dr. Russell.
Go right ahead.
I had a question on the branch versus unbranched, and you said the branch takes priority. I was
Yes.
just wondering how to identify the branch. Is that like those are not wedged or dashed?
No, so you can see right here,
Hmm.
this carbon right here is what you call a geminal carbon,
Okay.
where it's got two of the same groups on it. So
Uh-huh.
that's an example of a branch carbon. Uh, the tert-butyl is a branch also, but it's not geminal. So and when I say branch, what I mean is like if it's a geminal carbon like this, where you have a carbon right here, and then immediately attached to it you have uh two methyl groups.
Okay.
Does that make sense?
Yes, sir. And then
Oh,
can you talk about the other one again? Or what's the difference? I know I understand the geminal, but what was the other one?
this is what you call a tertiary butyl, which is a type of functional. It's a derivative of a butyl functional group, but it wouldn't be considered a branch point. A branch happens. Let me just write a quick. A branch happens like if I have a methyl group here, or if a methyl group here, or if I have on a chain two methyl groups like that. Those are what we consider branch points.
Okay.
Mm-hmm.
All right. Thank you.
Yeah, no problem. Great question. All right. Any other questions? I'll clean up this structure too before I send this because this is horrific. But all right, let me do this. Let's keep pushing with this same example. Actually, you know what? I'm going to shucks, come on, Russell. Let me go back. So I want to talk about diastereomers also, which are not enantiomers. They're not mirror images. However, they're still stereoisomers. Let's see if I can catch that. Okay. So with the enantiomer, somebody tell me again what the difference is would be between two enantiomers. What would the difference be as far as the configurations are concerned? Actually, let's go back right quick to here. What were our stereo centers here? S S R R S S. Is that right?
Yes.
What would they be in the mirror image? What would this one be? Here. If it's S in the original image, what would it be in the mirror image?
R.
R. Excellent. That would be R. This would be R. So with this following, everything would be reversed. This would also be R. Right. And then this would be R. I missed the R somewhere. Hold up. That would be R. And so with this. Where'd I
I
miss a
think
R?
the three
This
branch
way.
nitrogen.
Mm-hmm. I missed that one. That should be S, shouldn't it? Is that right? Wouldn't that be S? Because one of them over here was R right here. So that one should be S. But the point is, for the enantiomer, all of your stereo centers are going to be reversed. All right, we're good with that so far? All right. Let's look at let's look here. Let's talk about diastereomers. All right. Now, if in the enantiomer, everything changes, right? R changes to S, S changes to R because it's a mirror image. In a diastereomer, it is not a mirror image. And I'm just going to go ahead and paste this again. Right. So for this molecule, let's just say, for instance, that this is the original molecule, and then this is the A diastereomer of that molecule. Right. I'm just going to change that stereocenter right there. Do you see that? What's different? Everything else stayed the same, didn't it? Right? Did y'all catch that? I took this stereocenter right here. And I changed it from wedged or dashed to wedged. But I didn't touch anything else. This is what we call a diastereomer. It's not a mirror image. And you only change one stereocenter. Yes or no?
Yes.
Mm-hmm. All right. How many? So again, we said we had 64 total stereoisomers. Is that right?
Yes.
Yes.
So think about this. I want you to think about this. So we've already looked at the mirror image. For the diastereomer, how many can I go through and change one stereocenter at a time for each stereocenter? And this would no longer be S, by the way. It will be R. Right, because I changed it. But are y'all following that? So every one of those stereocenters, I could go in and just change one at a time. So I've done it here. Let me do another one to make the point. So which one do you want to change next or now? Or you just want to walk it down? Let's just change that one. Now that's S. Well, are y'all following that? Compare that to the original image here, where that H is on a dash. Now over here, I've changed it such that the hydrogen is on a wedge. But I haven't touched anything else. So I'm only changing one stereocenter at a time. And I can do that for every stereocenter in that molecule. Does that make sense?
Yes.
Mm-hmm. So how do I get 64 stereoisomers? How do I get 64 stereoisomers? What is it? So each one of my diastereomers, would it have a mirror image also?
Yes.
It would. And so that's where all your other stereoisomers come from. You may have a diastereomer that has a mirror image or an enantiomer. So each one of my diastereomers is also going to have a mirror image. And so that's where all of your other stereoisomers are going to come from. Like just altering one stereo center at a time. And then every time I change one stereo center, I could also create or draw the mirror image of that diastereomer. Right. So each time you alter one stereo center, you can also have a mirror image of that. So that's how you are able to get to 64 different stereoisomers, although we started out with this one image right here. All right. Questions. It's quiet. It's too quiet.
I have a question. So on the one of the stereo centers where there's a branch carbon, if
Mhm.
you were making a diastereomer of it, would you change both of the hydrogens or would you just change one at a time?
One at a time. You talk about for this one right here. Hold up. Sorry.
Yes.
Right there. I would only change one at a time.
Okay. Thank you.
Yeah, great question. Other questions? Anything? So let's kind of have a little bit of a recap. So an enantiomer is what? Somebody give me that definition.
A non-superimposable mirror image.
Non-superimposable mirror image. A diastereomer is what? Is it a mirror image?
No.
It is not. But it is a stereoisomer. It's just not a mirror image, right? It's still chiral. It's still a stereoisomer, but it's not a mirror image. So to draw a diastereomer, you only alter one stereo center at a time. And in order for diastereomers to be possible, you need at least two stereo centers. Right? You got to have at least two stereo centers in order to be able to generate a diastereomer. All right. Any questions about anything? All right. Let's go. Let's look at this other Paxlovid derivative, because when they give this drug to COVID patients, they actually give it in tandem. So you actually take both. How many? First of all, let's identify all the chiral centers present here. So let's do that first. That's the first skill we need to develop, is at least how to identify chiral centers. Then how to assign configuration. Then how to draw the mirror image, or to draw the diastereomer. So how many chiral centers are present here? And what can we rule out? Can we rule these rings out?
Yes.
Mm-hmm. All of those rings are full of sp2 hybridized carbons. So we rule them out. All right. What else can we rule out? Can we rule out all these CH2s? Sorry. Anywhere that there's a CH2 or a CH3, we can rule out. Is that right?
Yes.
Mm-hmm. This is a CH2 right here. We can rule that out. We can rule that out. What else? Oh, we can rule that out too. And that. All right. So now in all the sp2 carbons, all these carbonyls, we can rule them out because they're not sp3. If it's not sp3 hybridized, it can't be chiral. It could be, but it's not initially chiral. You can make it chiral by reacting it with some nucleophile and making it sp3, but we're not gonna get into that. All right. So where are my chiral centers? Let's find them. Is this one right here?
Yes.
It is. What about here?
Yeah.
Yes.
Mm-hmm. It is. What about here?
Yes.
And here?
Yes.
Yes.
Okay, good. Did I miss any? All right. The question now is, how many possible stereoisomers exist for this molecule based on the number of stereo centers that we've located?
$32.
It'll be 2 to the 4.
16.
Okay. 2 to the 4th. 16. I agree with that. 16 total. All right. Let's see about we got I'm gonna stop in 3 minutes. Let's assign the configuration to let's start here. Right. So obviously nitrogen here is 1. You agree with that? Because the groups are nitrogen, carbon, carbon, and then there's a hydrogen that's here on a wedge. What is that a red flag for? If you see your hydrogen on a wedge, what does that tell you right away?
You're gonna change the configuration.
Come on. That's right. You're gonna reverse your configuration. All right, so nitrogen is 1, and then you got 2 carbons, 1 bound to oxygen, and then 1, let me change the color on that. 1 bound to oxygen, and then 1 bound to carbon. Even though that carbon is in an aromatic ring, it does not take precedent over the oxygen. All right. So what's the priority? Which one is 2 and which one is 3? Is this carbon 2 on that side?
Yes.
And then this is 3 here. Yes.
Yes.
Mm-hmm. All right. Now, question: clockwise or counterclockwise? We just counted 3 in order.
Clockwise in order.
It's clockwise. Yes. However, H is up. Right. And so if H is up, that means that we have to reverse it. So it looks like it should be R, but because hydrogen is already on a wedge, it is what? S. Is that clear?
Yes.
All right. I'm gonna stop right there. Hopefully, prayerfully, we'll have class in person on Wednesday, because this is for the birds. I enjoy Zoom, but I much prefer to be on that clear touch board. But anyway, we're gonna stop here, and we'll pick up on Wednesday. I'll let you know in an announcement, one way or the other, whether it'll be virtual or whether it'll be in person. But it's my prayer that it's gonna be in person. So, any questions before we log out?